My name is Terry Quinn. I'm the Emeritus Director of the International Bureau of Weights and Measures on the outskirts of Paris at Sèvres. Our main claim to fame is that we hold the international prototype of the kilogram, to which all mass measurements in the world are traceable. We plan to change the definition of the kilogram so that it is linked to the constant of physics. This has been underway for many years in big labs with big experiments called watt balances. I'm going to show you today a demonstration model of a watt balance that can show you how, in principle, we can measure the weight of this without having to make links to the international prototype in Paris. So, how do I know this is 200 grams? I know it's 200 grams because if I put it on the balance, it weighs 200 grams. But how does this balance know it weighs 200 grams? And that's where we come to the link, which I will show you. We take a standard weight and put it on there. And this calibrates the balance. But where does this standard weight come from? This standard weight comes from multiple comparisons with other standards of higher level, right up to the international prototype of the kilogram that's kept in my lab in Paris. So why can't we continue to have the kilogram defined as the international prototype? Well, suppose we drop it. That's the answer. You can drop it, but if you put it on a balance, you might take a little bit off the bottom if you breathe on it. Since it is not related by the laws of physics to anything that we know is stable, it's an unsatisfactory standard, and in the long term we can't be sure that it's stable. I'm now going to show you how I weigh this 200 grams with this device called a watt balance. The first operation, we set this to 0. This micrometer that tells you that simply the position of the coil. I then hang this on and you'll see it moves. So I'm putting a weight on this lever which is pulling the coil of the loudspeaker up, and we're measuring by how far it moves up with this. I then turn on my electric current through the coil of the loudspeaker and I slowly bring it back up to the 0 again. So far, what we've done is exactly the same as what happens in this balance. In this balance, I make a measurement of current. In this one, I've made a measurement of current as well. But then things are different. So we now come to the second part of the experiment. I take off this weight, and then what follows is different from this completely. I now must connect this to my little Lego motor at the end. And the way I do this, a very simple operation. And then I switch on the Lego motor, and what you'll see is that this moves up and down. As it moves up and down, I'm measuring by how far it moves up and down with this micrometer. But at the same time, I'm measuring the voltage that comes out of the coil of the loudspeaker. And on this oscilloscope, you can see the voltage going up and down in exactly the same way as the coil is going up and down. I measure that voltage. But then, because I'm measuring the time as well, I'm measuring the distance. Because I'm measuring time and distance, I can calculate how quickly it's moving, the velocity. So I have two essential pieces of information, the velocity and the voltage that corresponds to that velocity. Okay, so how does all this work? How does the watt balance I've showed you actually work? Let me show you. If we imagine a simple balance on a knife edge, from one side we have a pan upon which we put our mass, m. The downward force on that is m times g, the acceleration due to gravity. We then balance that with an electromagnetic force. This is from the loudspeaker coil. And we have our coil inside the loudspeaker, and I draw a little diagram of a loudspeaker which looks a bit like this. And this is a magnet. The downward force from the current through the coil you can write as the current times B times L, where L is the length of the coil, length of the wire, that is in the magnetic field of strength B. But you don't know what that is. But you make these two equal. So you have I times the magnetic field times the length balances the mass times the acceleration due to gravity. This is like any electronic balance today, and they calibrate it, as I showed you earlier, by taking standard weights, and in that way they calibrate what this is. We do it differently. We do it differently in the second part of the experiment. So it's the same balance, that's our pan, but we don't have a mass on it this time. Here we have our coil, magnetic field, the same magnetic field, and then we move this up and down, which you saw, moved up and down. And if it moves up and down, what comes out of this is a voltage, V. And because it's moving up and down in a regular way, the voltage looks a bit like that. But the voltage equals the same magnetic field times the same length times the velocity, how fast it's moving, and we measure the velocity. So here we have an equation, voltage equals magnetic field times length times velocity, and our previous equation, you remember, was electric current times the field times the length equals that. We can combine these two together. And if we combine these two equations together, which is a very simple operation, we end up with a very simple equation. We have mass times acceleration due to gravity times the velocity equals voltage times the current. And you remember, we measured the velocity because we had our oscilloscope picture. We measured our voltage. We measured the velocity because we knew how far it was moving and what the time was. And we measured our electric current. So we measured that, we've measured that, we've measured that. Acceleration due to gravity we know, and therefore we can calculate the mass. Final question, what about the Planck constant? Well, modern physics now allows us to link these electrical quantities to the Planck constant that we call h.